This is an interim progress report on some research that has been running since about 2019. These are preliminary results. This doesn't even have a name yet because this is so new. But what I'm doing is I'm trying to prove that I can hack into your computer by laser beams. Some years ago, a friend of mine and we worked on the problem of information leakage from optical emanations, little blinky lights on computers. We proved that they actually leak information. They leak quite a bit of information, talking cryptographic keys, cryptographic plain text. We published an influential paper on this, and so far it's been cited several hundred times by other researchers. It's an active area of research. But a couple of years ago, I started to wonder if I could go the other way. Now, that seems kind of silly. These are light emitting diodes. But it turns out that, yes, you can go the other way. If I pump enough optical energy into a front panel LED on a computer, I can generate a small electrical current that goes backwards through the circuitry of the computer and maybe affects its operation. You may have seen this demo that I brought to TechConfluence a couple of years ago, or you may have seen this other demo when it was quite a bit more primitive. But this is a classical covert channel. In computer security, that means it depends on having an insider threat. There needs to be some malware running on the system that's listening for a signal and allowing the signal to come in. That's cool and all, and I made it work, but it kind of feels like cheating because you have to hack into the computer by conventional means first, and then after that, the laser trick works. Well, that seems like cheating. I wanted to do this to a completely unprepared computer where there is no insider threat, there's no Trojan horse, there's no malicious code already running on the system. I don't have to make that assumption. I wanted to do this to a computer that's 2 miles away and has not been prepared as a perfectly ordinary computer. Something I should have said at the beginning, I am not developing attacks. I am developing defenses. But I got to understand where the vulnerabilities are first. So I went looking, I got it to work about 2 years ago with the presence of an insider. The target needs to be actively listening for communication. And this is not an unreasonable assumption by info security standards. Stuxnet proved that in Iran. You can almost always get the malware onto the system, even if it's air-gapped. But still, it felt like cheating because you have to hack into the system by conventional means first. And I didn't really like that. I went looking, I found this because I went looking for it. You may have seen this figure before if you've been to a previous TechConfluence, but I simplified this figure a bit. I was looking at the relationship between information and energy. And if you think of a computer virus it's all information. There's no energy component to it. But if you think about if you drop a bomb on a computer, that's a pretty effective way of shutting it down. It's all energy. There's no information component. A little bit more subtle than that would be if you shut down the electrical grid. That's a pretty effective way of shutting down a data center. If once their emergency generators run out of fuel, they're not going to be doing any more computing. But I began to wonder about this upper right-hand quadrant 1 in this graph. There's nothing there. what kind of a directed energy cyber weapon might you imagine that is both high energy and high information content? So I went looking for it, and I think I found it. Whatever this is, it doesn't have a name yet. This is new. I brought a small demonstration, and I'd like to show you this working in real time. Can you see my demo? Yep. Okay.
Demo is showing there. And sorry for the remote audience. I guess the slide kept showing the first one, but we'll post the slides afterwards.
Maybe they can see it. I will try to do that. Okay. Can they see it now?
They can definitely see that camera that's pointing at your demo. So I think that's pretty good.
Yep, we can see it.
Yes.
This is a fairly
Yes, he's still stuck on the title slide. Or not.
I think the slides aren't.
Oh, okay. All right, I think you can hear me if I stand over here.
That's much better.
Okay. This one, sorry. This is accessibility. In real time.
Yes. So now I can't find, oh, there's the.
There. Okay. Please don't bump the table because this all has to be aligned carefully. Okay. Can you hear me? Yes. Okay. This is a
Yes.
fairly simple computer, but it's enough to demonstrate my concept. This is the kind of control computer that you would find in a water treatment plant or a factory or a power station doing process control automation tasks, reading sensors, controlling the position, opening and closing valves, that kind of thing. It has not been prepared. It's a perfectly ordinary computer. There's no malware running on it. It is simply it's simply doing its computery stuff. There's no malware running on it. It has not been hacked into already. It's just sitting there not expecting anything. I'm going to hit it with an ultraviolet laser at 405 nanometers. It doesn't take much, but you can see it just stopped. I just crashed that computer remotely without touching it. That's all I can do so far. Let me reset it. It's not much of an attack. It's not much of an attack. All I can do is patch the thing. But I am very close to being able to execute arbitrary code. I can subvert instruction decoding. I can affect memory addresses and data. I can subvert memory accesses, instruction decoding, and branch instructions. It is easy to write arbitrary-ish code up into high memory because all you have to do is set the high bit. Limitations of this method are I can only set a bit. I cannot reset it. Okay. The reason I brought this here today, even though this is still a laboratory demonstration stage, is that it's not a practical attack yet. I wanted to get your feedback on how I talk about this stuff because I'm not very good at it yet. Limitations on the method. I can only set a bit. I can change a binary 0 to a 1, but I can't change it back again. That means that I can write arbitrary-ish code up in high memory. because I can only change a 0 to a 1, but not the other way, I have access to about half the instruction set on the computer. So maybe I can do some things, but I can't do other things. But I can write arbitrary-ish code. And it's easy to write to high memory because all I have to do is toggle the high bit and it automatically goes up in high memory. So I can, oh, and I have to be very careful not to crash the running program accidentally because I need it. I have to subvert its memory operations in order to do this trick. So it's a two-stage attack. I write arbitrary-ish code up in high memory until I've got enough up in there to branch to it and run it. And then the first thing that code does is it runs fix-ups on itself in order to correct any deficiencies that I was not able to write directly, and then it branches to the arbitrary code and runs it, and I have full control. I think I'll manage to do that in a few more weeks of work. The next thing after that is to prove that I can do it on a computer that somebody else designed. It's you know, anybody can hack into a computer that they designed, but let's see you run it on hardware that somebody else designed. That's going to be probably a few more months of work. I'm working on it and I'm making some progress. But I've had to move to much more powerful lasers than I was using before. I'm up into the 10 to 40 watt range now. These are cutting lasers, and I have to be kind of careful not to melt the LED that I'm targeting. But I'm working on it, and I believe that the method will work, probably up to a range of about 2 miles. That's going to be it. That's assuming optics probably about the size of a trash can, but I think based on atmospheric transmissivity, quantum efficiency, and angle of incidence, I think I can probably make it work up to about 2 miles. But that's probably going to be my next demonstration, because this is not fully working yet. I only got this working a couple of weeks ago. This is brand new. It like I said, it doesn't even have a name yet. But maybe this will go into a good security conference in another year when I have it working better. But you're seeing it as it exists now. That's it. Any questions?
Yeah, that's anything else. Question from the audience about kind of how this works, which I remember from you explaining at a previous demonstration of it.
This is a phenomenon that was discovered way back in the 1970s, but it hasn't really been used much. There's a general principle in physics that any process that will run in one direction will probably be able to run in the other direction. It's called time reversibility. If you supply enough energy,
Should unmute this mic.
yeah. Okay, can you hear me now? There's a general principle in physics called time reversibility that any process that'll run in one direction will probably run in the other direction if you supply enough energy to make up to make the equation balance. LEDs in reverse bias, reverse electrical bias, can act as teeny tiny little solar panels. This is actually a general principle. There's a professor in Italy, I believe, who's flying drones over fields of solar panels, solar generating panels, and actually with a video camera and some very narrow band optical filters, looking for malfunctioning solar panels, because they actually glow. A malfunctioning solar panel in a farm of solar panels, a malfunctioning one with small cracks in its surface, in the surface of the silicon chip, actually goes into reverse bias and it begins to emit light. It's up in the infrared, so you can't see it, but a digital camera with the right filter can see it. So she's flying drones over fields of solar panels looking for malfunctioning solar panels that way. The same kind of principle can be used with LEDs. If they're in forward bias mode, they emit light, but in reverse bias mode, you have to pump a fair amount of energy, optical energy, into the LED in order to reverse it and generate that electric current. But let me see if I can go to my backup slides. I spent a lot of time poring over schematics and looking for likely components that I can subvert. The nice thing about LEDs is they often come in groups in a schematic. And when as you're looking at this schematic here, these two LEDs are connected to a common power rail. And that means that if I pump enough optical energy into one of those LEDs, it will go backwards and reverse bias the other one. And the thing about LEDs is, well, they're diodes. If you can put an LED, if you can put a diode into reverse bias, you can use it like a switch. So I can begin to switch the electrical current around in this circuit the way that I want it, the way where I want it to go. It's very difficult because you can't design the circuit that you want. You have to work with what's there. But essentially, my method is I will zap one of those LEDs with the laser, so in order to put the one next to it into reverse bias mode, which turns it into a switch, kind of like a transistor. So I can use that in order to modify the circuit. And so far I've proved that it does work, and the electrical current is getting far enough back into the CPU that it's beginning to affect instruction decoding and memory address and memory data, memory accesses. So it's possible, B, it's controllable, and C, the timing is absolutely critical. I need to establish a phase lock on some kind of visual indicator of the state vector of the running program. And usually that's just another of the front panel LEDs. So in practice, what this will look like is probably a high-speed video camera focused on the system, watching the behavior of one or more of the LEDs on the front panel. And as soon as it sees a pattern that it wants, it fires the laser. One interesting aspect of this is it doesn't matter if the LED is on or off. It doesn't matter if it's lit up or not. The effect still works. I can zap an LED that's lit up just as well as I can zap one that happens to be dark at the moment. I don't know much about this yet. This is brand new, and it's what can I tell you? Eventually I'm going to write another paper about this, but it's not there yet.
That's great. There's definitely more questions, but I think we'll have to stop there. We'll wrap up here. Thank you very much, Joe.